Hello, my name is Samay Patel, and this is my Physics 2211 Motion of a Falling Object lab report. And this is the second lab that we've performed in Physics 2211. To understand this report, we have to understand the goals of this report. And these are to record an object moving in free fall motion and use the program tracker in order to create an experimental model for the data, create a theoretical model using only the force of gravity, create a theoretical model using Newton's second law and applying the force of drag to said object, and perform analysis on the three models and compare and contrast the similarities and differences between them. To understand the concepts in this lab, we have to understand the background information behind them. To understand these, this must be Newton's second law as well as the forces of gravity and drag. To understand Newton's second law, we must understand that for velocity to change, there must be a net force acting on the object. And this experiment follows the results of the motion of the falling object, so we should expect a net force, aka change in the constant velocity. So the equations in this case are Newton's second law, which is V final is equal to V initial plus F net over m times change in time. Force of gravity, which is F of g, which is 0 times mg, and this is the whole vector format, but in this case g would be equal to negative 9.8 meters per second squared, and the force of drag, F of d, is equal to 0 bv squared, and then the b cap will be shown later. So the experiment, find an object and record it moving in free fall motion, use the application tracker to obtain experimental data about the object, and use this data to create an experimental model for the object. Using provided glow script, create two computational models. One model should use only the force of gravity, and the other model should use the force of gravity and drag. Then compare the models and record any important observations. So to start, this is my tracker, and as you can see, this is the object that I chose was a bowl that fell down. So I didn't actually use all of this. I considered a time frame that started a little bit in the middle of this, since I had a little bit of a technical issue with tracker. So this was the experimental data model that I collected. This was the time compared to the position overall. And this was the glow script that I created. As you can see, that this was the given code for us. This was the ball's mass, or the system's mass. This was the initial position, the initial vector that I chose, the time, the depth, the step, the magnitude. Now the experimental drag force that I calculated, that B in this case, was 0.033. But of course, when you're only considering the force of gravity, B would be 0.0 in this case. And my entire experiment was about just under a second, so I considered t is less than 0.9. Obviously, this was the F of g calculation. This was the force of drag calculation, and F net is equal to F of g plus F of d. This was the update formulas, and then obviously, this is how the experiment was performed. So now the theoretical model only using gravity shows a much more of an exponential curve. It looks almost parabolic, as you can see. Compared to the force of gravity and drag, this shows much more of a linear model of the position. So you can see that the only gravity model goes down at a much faster rate than the force of gravity and drag acting together. So the comparison models, so I compared the experimental model that was taken from my data from tracker and compared it to both the force of gravity model and the force of gravity and drag model. As you can see, the gravity and drag force model are much closer. The force of gravity, only the force of gravity model is much more, it's much more bigger. So with the information, as you can see, that this one is much more consistent. It accounts for drag force and gravity force, and it creates less error in the experiment. So some observations that I took from this were that this is due to the net force in between the two models. The net force for the only gravity model is much higher. The difference is when the force of drag is considered, which reduces the overall force and gives us a lower velocity and lower falling speed. So what does this mean? So for examine a velocity over time, predict anymore, where is a terminal velocity essentially? This would be closest to 0. There is terminal velocity on the drag and gravity force model. This can be seen in the asymptote, and since forces are equal in this case, the net force is 0. So for the what if, in this case, if it was initially thrown instead of dropped, it'd be different because the terminal velocity would be reached faster. This occurs due to drag force being reached faster when there's a higher velocity. And these models, I compared them in glow script with the higher velocity, and it shows that the terminal velocity is reached at a much faster time. Thank you for listening.